Hello everyone. Today I am going to discuss to you the third scheduling method. We have the linear scheduling method commonly known as the LSM. So far we have learned two different scheduling methods. The first one is the Gantt chart. The Gantt chart is a simple type or a particular scheduling method that requires only few activities. However, the linear scheduling method become a important scheduling method provided that they go in conjunctions with other scheduling techniques such as developing the S-curve. So the Gantt chart will be very important. You will see that as we move on to the project controlling. The second method that we've learned is critical path method. The critical path method, or commonly known as the CPM, it is commonly used and it is popular in any types of project. However, it is commonly used for vertical construction. So that's where we use the critical path method. Now, throughout the semesters, we've learned the manual calculations of the CPM as well as we use the computer base. In the manual calculations, you've learned how to draw the network diagram as well as to perform the forward and backward calculations. So with that, we're now moving into the third scheduling method. We call it the linear scheduling method. So again, LSM is commonly used for projects with sequences of repetitive activities. These are projects that are usually part of the third sector, which is known as the infrastructure or the heavy civil, such as constructions of roads and highways and bridges, or even high-rise building as well too, provided that each given floor of the building have the same nature at its given level. Now we have also sewer lines or levees or dams or canals or tunnels. We can use the linear scheduling method. So if the Gantt chart, which was first introduced in 1918 by Henry Grant, the critical path method, which was first introduced in late 1950s to early 1960s, the linear scheduling method is a unique means of a resource leveling or allocations through the visual representations of the graphs. Making use of the LSM, we will be able to identify which activity that can create problems or intersections of those lines, which give us an idea that there will be some sort of problems as those lines cross each other because of plotting those lines, and that will prompt us as a project engineer to make decisions later on. Alright, so there are several steps in linear scheduling method. The first one is to determine the work activities, pretty much the same as any given scheduling method. The first step is to perform WBS, or the work breakdown structure, which is an organizational tool that allows us to break the project into smaller tasks or activities. So that's the first step. Then the next step is to determine the duration or the activity production rate, commonly known as the PR. How quick a particular task will be accomplished, will be finished. So we need to figure that out. As long as we know how much, that is a quantity. How many, that's the Q. And then the length of time to finish them. So we just need to divide those two. That will give us the productivity rate. Otherwise, we could also determine the durations knowing the quantity and knowing the production rate, which we just divide those two, and that will give us the T, or the durations. The next step is to sequence the activities. Once we break down the project into various tasks or activities, we are going to identify which activity needs to be done first, which activity will come next, and which activity can be done at the same time. That is what we call as sequencing or In other words, logical relationships that we've learned in critical path method, such as the finish to start, start to finish, finish to finish, or start to start. Alright, so this is a graphical representations of the linear scheduling method. Now, simply drawing a particular line to represent a given activity with a calculated starting point and a calculated ending or finish date of a given activity. So the slope that is created by the time, that is the duration, and your quantity of work, that is what we call as the productivity rate. If you know how much okay, you're going to do divided by the given time, and that will give you this diagonal line, which is the productivity rate. Okay, it's a very simple space time diagramming. So it is a space-time diagramming because they are being plotted time against a given quantity, or in our case, because it's a horizontal construction, it is the location. All right, so how do we draw the curve, or how do we draw the line in LSM? Of course, first is calculate the productivity rate, or we need to calculate the duration. So I need to clarify this one here, because sometimes it gives us the PR and it gives us the how many, that's the quantity, then leaving us to calculate the durations of a given activities. Once we determine the durations, the next thing you have to do now is to determine the buffer. The buffer is pretty much the same as the lag time that we've learned in the critical path method. The lag time is an amount of time, or the flow time. It is the amount of time that we need to wait okay, after the completions of a particular activity. Say, for example, a concrete slab. We cannot build the framing or the wall not until we wait a certain period of time until the concrete has cured. Otherwise, we don't want to build a wall while the concrete is still in green state. So we need to make sure, and it's a requirement of the code, and it is recommendations by the American Concrete Institute, that we need to wait for a certain period of time until the concrete has hardened, okay, before we could move on to the next step. Alright, so in the case of the LSM, we need to calculate what they call it the buffers. A buffer is the amount of time that's split up, or amount of time that separate a given activity in order to prevent any intersection of the line along the way. Okay, intersections either on the start or intersections on the end or on the finish, or anything in between. Why is that? Well, the purpose of the buffer, in order to eliminate any inefficiencies on your resources, because if you're going to bring in your resources sooner, what will happen is that a particular activity may catch up on the previous activity, and what will happen then is that we will make our workers to sit down or to wait, and that's become inefficient. Or if you're going to bring in your resources to the job site and they're not ready yet, what will happen is that we will ask them to wait, and we are already paying them, and that is an inefficient way to do it. Alright, so to figure out if we will be calculating buffers, this is the keynote here. Okay, if the durations of the previous activity is greater than the durations of the activity in questions or the current activity, then you are required to calculate the buffer. If the durations of the previous activity has a lesser duration as compared to the activity in questions or the current activity, then you don't need to calculate the buffer. So again, I repeat, if the activity of the previous activity has a greater duration than the activity current or activity in question, then you are required to calculate the buffer. If the previous activity has lesser duration than the current activity, then you don't need to calculate the buffer. Only if the previous is greater than the current activity. So that is your key. So which means that once we calculate the buffer time, that is the amount of time that we need to separate the start and the start of the next activity, unless otherwise in a given problem will give us a minimum buffer between the start and the end or anything in between. All right, so this is the case here. This is a graphical representation that if you are going to bring in your resources and start an activity B, along the way your resources or your manpower will be able, because probably they are faster, they're able to catch up somewhere or sometime. Okay, so what happened is that at this particular point we will make your resources for your activity B to wait, so they become idle. So in that case, we will let your workers to sit down or do something, okay? And that is inefficient. We are already paying them, okay? So make sure that we avoid any of these intersections. So that is the goal of the buffer, to get away any of those intersections. All right, so in this particular case, in order to avoid that intersection, we delayed or we move your activity by a certain amount of time on the finish date. Okay, so it creates here now the separation of those two, getting away with that intersection. However, by moving your activity B, make sure that you need to choose or you need to calculate the optimum amount of starting date or the finish date. Remember, optimum, because if you just going to just choose whatever day that you want to start, as long as you separate them, well, you may end up having a duration that is longer than it should be. Remember, the time that complete the project is related to the indirect cost, okay, or the overhead cost of the project. The longer the project, the higher the amount of your indirect costs. So that's another thing that you need to watch out for this. All right, let's go and take a look at this first example here. And by the way, I uploaded a supplementary document in Blackboard that you can download it and be able to read and look at to follow the sequence and how to calculate them. I explain every step on that particular document. If you don't follow here on the PowerPoint on this video, you can always go back into your supplementary document that will help you and guide you going through this particular problem here. Alright, so we have here a particular problem. It has 5 different activities: excavating a trench, laying a sub-base of gravel, laying a concrete pipe, backfilling, and compacting. And you will notice that there is a given quantity, that is the location, which is 1,000 linear feet, and that the productivity rates, there are given productivity rates here: 100 for activity A, 125 linear feet per day. For activity B, 75 for your C, 200 for your D, and 150 linear feet per day for the last activity here. Now we are asked to create a diagram, and we need to, again, the problem specifies here that there must be a 1-day time buffer, a separation either on the start or on the end of a given activity, that they must be separated at least 1 day buffer. All right, so to do that, again, below this slide here, there are explanation. So I want you to open also your PowerPoint, or again, you have your handouts, supplementary document that will guide you how do we calculate those numbers. Okay. All right. So again, the second column here, those are all given. Okay, it is given on the problem, and to calculate the duration, all these 3 column here, those correspond to the values that we need to calculate. So how do we calculate the durations of the first number? Our formula here is D is equal to the quantity divided by the productivity rate. So do we know the quantity? Yes, it is given. and that is 1,000 linear feet. So that's your Q divided by PR. PR are given here. So again, 1,000 divided by 100, that gives you 10 days. 1,000 divided by 125, that gives you 8 days. 1,000 divided by 75, that gives you 14 days. 1,000 divided by 200, that gives you 5 days. 1,000 divided by 150, that gives you approximately about 7 days. And by the way, class, if you obtain a decimal values, I encourage you to round it up to the next whole number, because we will be paying our workers, especially if the project is far. Okay, as you bring in your resources, we will be paying them a full day. Well, it's a civil project. Okay, all right. So how do we calculate the start and the finish? Just like on the Gantt chart and on the critical path method, we are going to use the end of day convention. For most textbook, they use the end of day convention. Say for example here, we start on the 0 day. That is only on the paper, the calculation. In reality, the start date of activity A is the next day, which is the 1st. Why do they do this? Why we need to start at 0? To make our calculations simple by adding and subtracting. Because here, 0 plus 10, of course, it will finish on the finish date. Now, if we're going to make use of 1 here, and we add 10 days, you finish on the 11th day. So which means that we have 11 days for that particular activity? Definitely not, because we are supposed to be finishing in 10 days. So again, for make it simple calculation, we begin at 0. However, in reality, we start the next day. That's why they call it the end of day convention. So in this particular case here, we start on the 3rd day. However, in reality, that begins on the 4th day. Okay, so say for example, we begin on the 4th day. When we count that, 4, 5, 6, 7, 8, 9, 10, 11, that gives you actually 8 days duration. Alright, so let's start. So we're going to begin first activity 0 and finish on the 10th day. That is 0 plus 10 is equal to 10. Alright, let's move on to activity B. So how did we get that? Start of 3. So again, notice, as we had previously, on the previous slide, we need to calculate the buffer time if the previous activity has greater duration as compared to the duration of the activity in question. So in this case here, activity A duration is greater than the duration of activity A. Activity B. So in that case, you are required to calculate the buffer time. So how do we calculate the buffer time? It gives you here the formula on this particular slide here. Time buffer is the duration of the previous activity minus the duration of the activity in question. So going back to the table, so it is 10 minus 8, that is equal to 2. Which means that we should begin on 0 plus 2 should be on the 2nd day. Woo! What happened here? Why we start on the 3rd day? Let me explain that. So if we are going to begin on the 2nd day, because of our buffer calculation, which is 0 plus 2, what did we get at 2? The buffer time, which is 10 minus 8 equals to 2. So we should begin here on the 2nd day. So how come I didn't begin that on the 2nd day? Alright, take a look at here. If we begin on the 2nd day, plus 8, what is the sum? The 10th day. So if it will finish on the 10th day, what will happen? They intersected to your activity A. Remember, the problem tells us that you need to provide a minimum 1 day buffer. So in that case, if we have a 1 day buffer, we need to extend the finish date of activity B by 1 day so that it will not intersect your previous activity with its 10th day. So we have 10 plus 1, we're going to end on the 11. So 11 minus 8, we're going to begin on the 3rd day. So again, supposed to be, we are going to start on the second day here. So where do we get that second day? Because the buffer time, 10 minus 8, that's 2. 0 plus 2, that's a buffer time, should start here the second day. However, if we're going to start on the second day, for your activity B plus your duration, it will end on the 10th day, which will intersect your activity A, which again the problem tells us that we need to avoid an intersection. So in that case, we need to separate your activity A and B by 1 day. Oh wow, so where did you get that 1 day? So it says here that we need to provide 1 day. Alright, so 10 plus 1, that gives you 11. So which means the activity B should end on the 11th day. 11 minus the duration, so you will start on the 3rd day. You got it? Alright. Let's move on to your activity C. Your activity C, we do not need to calculate the buffer. Why? Because the previous activity, the duration is less than the duration of the current activities. In that case, you do not need to calculate the buffer. So in that case, we need to start the next day. So that's why we have here the next day, which is the 4th. 4 plus 14 equals 18. Get it? Alright, let's take a look at your activity D. Your activity D has a duration of 5 days. Notice again, what do we have on the previous activity? 14, which means that it is greater than the duration of the activity in question or the current activity. So what are we going to do? We are going to calculate the current or the buffer time. So the buffer time will be 14 minus 5. That gives you 9 days, right? So 9 plus 4, that is the start of activity C. So 4 plus the buffer time, which is 9, should start on the 13th. Oh, look at this again. Why are we starting the 14th? Let me show you again. If we are going to start on the 13th day, plus your duration 5 days, it will finish on the 18th. And notice again, your activity C ends on the 18th. It will intersect your activity D. So to avoid that, what the problem tells us, we need to separate with a minimum buffer of 1 day. So in this case, we add 18 plus 1, that's 19. So we need to make sure that your activity D will end on the 19th day. So 19 minus 5 is equal to the 14th day. Alright, so again, supposed to be we start activity D on the 13th day. However, when we add the start 13 plus 5, it will end on the 18th, which will intersect your activity C. That's the reason why we move the finish date to the 19th day. So 19 minus 5, that gives you 14. And that get rid of any intersection between those two activities. Let's go to activity E. Your activity E has a duration of 7, and the activity of the previous activity D has a lesser value. In that case, we do not need to calculate the buffer time. So in this case, we need to start the next day, which is the 15th. 15 plus 7, that gives you 22. Very simple, okay? Take note, your key here is you begin the first activity at 0 unless otherwise you are specifically started at a particular day. The second thing that you need to take note is the buffer time. So the buffer time is just the difference of the previous activity minus the current activity. Okay? You only calculate the buffer time if the previous activity is greater than the duration of the activity in questions or the current activity. The third thing that you need to keep in mind is that we need to avoid an intersection in the start or on the finish time. Okay, if that is the case, and if the problem tells you that you need to provide a minimum buffer, say 1 day, make sure that you have to adjust the finish date, and then subtract the finish date to the duration, and then you will be able to calculate the finish time of the given activity. Again, I provided a supplementary documents that you can read. I provided the example there. I provided explanation and step-by-step procedure, and hopefully that will help you if you miss any of the steps that I'm telling you here on this video. So the next thing that you're going to do now is to draw the diagram. Given all this calculation on this table here, what you need to do now is just draw them on the graph. So you need to create a graph. You can use Excel or you can use the Word file to draw them. Okay, so in this case, we start 0 for your activity A and end on activity 10. Okay, so notice here the 0, 10. Alright, and notice now it's very clear here, none of those lines intersect, and that is what we want. Very clean. And the optimum duration of the project is 2. Now, if you are just going to move your activity B and finish to wherever you want, you may end up longer days, and we don't want that as well too. The longer the project, the higher the amount of your indirect costs. Okay, and another thing, by contract, there are certain durations where you need to finish the project, so you need to make sure that you need to create a schedule that will provide you the optimum schedule date, and that's the reason why we have this. Okay, all right, so you just need to draw them on your second activity that's represented by the red line. We begin on the 3rd day and we end on the 11th. So here, and notice here we provided that with a buffer time of 1 day. The same thing also with your activity C and your D. So again, just draw those lines, making use of insert line command, no graph. It is just drawing a line from a given coordinates or point along the x-axis, that is the time, and the quantity on the y, that is the last one here. This is your 500 feet, okay, 1000 linear feet. Okay, so that is the values that we have. Okay, all right, so that's how you are going to draw the graph. All right, let's move on to the second problem. The second problem here provides us a given quantity, 500 feet, and provide additional information. Trenching will be completed in 5 weeks. So it gives you here a duration for the first activity, and it will last for 5 weeks. The second one, installing pipe, will start digging after digging 100 feet. So there is a specific time to where we will start the next activity. That is after they dig 100 feet. So how many days will that be? How many weeks will that be? And I'm going to show you that calculations. And there is a given productivity rate, how fast they're going to lay down the pipe. And then and backfilling can begin after 3 weeks from the start of installing pipe, which is 125 feet per week. Develop a linear schedule for the project. What is the project duration? Okay, of the project. Alright, so this is our table here. These are the productivity rate that are given. We are going to calculate all of this. Okay, this particular values. Alright, so let's take a look at the calculations here. Alright, so how do we get at least 25 here? Alright, so first, we need to calculate the duration of activity A because it's not given. So it gives you here the quantity and you have here the completion time. So 500 feet divided by 5 weeks, that will give you 100 feet. So 500 divided by 500 divided by 500 divided by 5, that will give you 100 feet per week. The rest, 75 and 25, those are given. Okay. All right, let's calculate the duration. I converted this in day, assuming that in a given week they're going to work for 5 days. All right. So how do we calculate this 25? So it says here that your trenching will be completed in 5 weeks. So 5 times 5, that gives you 25. So here, 500 feet, that is your quantity, divided by 75, that will give you 7 weeks. When you calculate that, when you calculate it should be 6.67. We round it up to the whole next week. Excuse me. And that gives you 7 weeks. 7 times 5, and that gives you the 35 days. Now for the next one, 500 divided by 125, that gives you 5 days, 4 weeks. So 500 divided by 125, that is 4 weeks. 4 weeks times 5, that gives you 20 days. So again, I converted the week because this one here says per week. That is a unit. So what you have when you divide them is in terms of weeks. So that weeks multiplied by 5 days per week, that is the working day in each of this. Alright, so let's calculate now the start and the finish date. Alright, so here, if give us here the 0, we're going to begin 0 plus 25 days. It ends on the 25 days. Alright, the next one now is the starting date of the installed pipe. I want you to take note, it says here, the installing pipe will start after digging 500 feet. So how many days will that be? So if it is 100 feet, how many days will that be? So what you have to do is to figure out how many days you know the productivity rate, right? So 100 feet divided by 100. That means that is 1 week, right? So 1 week, that corresponds to 5 days. So for the next activity, we can begin on the 5th day. Alright? So that is again beginning the 6th day. But 0 plus 5, that's why we have there the 5. Again, you may ask, how do we start at 5 days? Because the problem tells us that we can begin installing the pipe after 100 feet. The only thing we need to figure out is how many days will that be. So what you need to do is your productivity rate and that 100 linear feet, you divide them. So 100 linear feet divided by 100 feet per week, that means that they will be able to dig 100 feet in 1 week. So 1 week corresponds to 5 days. So 0 plus 5 days, and there you go. It will give you that particular duration. Alright, so with that, it gives you here the 40 days. Alright, so the next one now is backfilling. Notice that there is a greater in duration, which is 35 and 20. Okay, so 35 minus 20, that gives you 15 days. So if we're going to add that 5 plus 15 days, that will give you 20 days. But I want you to notice here, it says here, they can begin after 3 weeks. So that is 3 times 5. That also the same as 15 days. So 5 plus 15 days, it should begin on the 20th day, right? But take a look at here. If we're going to begin at 20 days plus 20, what will happen is we will end on the 40th day, which means that we will intersect your installed pipe. And we don't want that to happen as well too. So in that case, we're going to move 1 day for your installed pipe, finish date of backfilling by 1 day. So 40 plus 1, 41 days. 41 minus the duration, that gives you 21. Alright, let me clarify here. First, we need to calculate the buffer time. Why? Because the duration of installed pipe is larger than the backfilling. So 35 minus 20, that is 15 days. 15 plus 5, that gives you 20. But wait, we need to look at also the conditions of the problem. It says here that we need to begin the backfilling after the start of the installed pipe. So how many days will that be? That is 3 times 5 days working. That is 15 days. Well, the buffer and the one that's given by the problem have the same number of days, which again 15. So 5 plus 15, it should begin on the 20th day. However, notice that I didn't begin on the 21 days. Why is that? Because when we add 20 plus your duration, it will end on the 40th day, which will intersect installed pipe. So what are we going to do? The remedy for this one is to add 1 day to separate the finish date of your installed pipe and your backfilling. So I add 1 day, so that will give you 41 days for your finish date for your backfilling. 41 minus 20, and that will give you now the 21 days. So again, on your handout, I provide an explanation in each of those given steps. But I encourage you, if you don't understand them and if you need help, please email me, okay, so that I'll be able to guide you on this, okay. But as always, you have your supplementary documents that you could always look back and review and examine. I provided an explanation at every given step why we got those numbers, okay. And if you have any question, please let me know. I will do my best to help you. Alright, so again, once you completed the table, the next thing you have to do now is to draw the line, okay. So in this case, I have your activity A, activity B, and your activity C. So I plotted them. We have here the first one, 0 to your whatever the end day, which is your 25 days, okay. And that particular case, it should be 0 plus 25. Okay, I want you to move that. I thought I moved that. It should end here. Alright, so I want you to correct that. I'm going to correct that on your handout, but that should be on the 25 days, and then your next one will be on the 5th day to your 40 days, and the next one will be on the 21 to your 41 days. Okay, this is 41, this is 42 here. Okay, so I want you to correct your activity A. It should end on, say here, 0 plus 25, that is 25 days. Okay, it should be on the 25. I am going to correct that on your supplementary documents. Alright, so as always, okay, just email me if you have any question. Alright, so this is our third scheduling method. We call it the LSM, the linear scheduling method, and it is commonly used for horizontal construction. It only involves few activities. The first thing you have to do is to break down the project. Second one is to sequence them, determine the duration, and then you have to calculate the buffer. Again, the buffer is only being calculated if the previous activity has longer duration than the current activity. Then of course you need to calculate the start and the finish time. Watch out for the given minimum. We need to separate any given activities. We need to avoid any intersections of the line, either on the start, on the end, or anything in between. Okay, the goal here is to create a schedule that has the optimum duration. I want you to keep that in mind, because in every given project there is a given end and start and ending. And if you don't comply with that one, you are subjected with a certain penalty or fee, commonly known as DLD, liquidated damages. Again, guys, if you have any question, just send me an email. You have your supplementary documents that will help you with your calculations if you have any questions. All right, thank you, guys, and I'm going to present next the program evaluations and review technique. All right, guys, thank you.